Let's talk about the mean value theorem. It's a theorem in calculus that allows us to prove lots of other things in calculus in a fairly elegant way, so lots of pure mathematicians really like it. It's kind of interesting. It tells us that a particular point exists, which we'll talk about later, but it doesn't really tell us how to find it, so it can be a little bit computationally disappointing. But let's at least talk about what it says. So let's say we have a sprinter, and at time 0 seconds, right before the starting signal goes, their location is 0 meters on the track, and 1 second later they are at 8 meters down the track. What would you say was their average speed from time 0 to time 1? So pause the video and write down a formula for what their average speed was. All right. So I'd say their average speed would be the total distance traveled divided by the elapsed time, how much time it took. So how far did they go? Well, they ended up at 8 meters and they started at 0 meters. They ended up at 1 second and started at 0 seconds. So it'd be 8 over 1, or 8 meters per second. Do you recognize this kind of computation? That's just a difference quotient, except it's over a fairly long time interval. I mean, in a race, especially a 100-meter race, 1 second could be a long time. So it's basically a difference quotient on a long chunk of time rather than a tiny, tiny chunk of time like we used for derivatives. So let's write that down. I guess we'll call it a non-tiny chunk of time. It'd be good to diagram the situation, right? Or make a graph, so let's do that. Think about how you might sketch a graph of what's going on here. Well, usually when we have time in the problem, that's the x-axis. So we'll have time from 0 to 1 second. And position 0 meters to 8 meters. And what do you think the curve of where the runner was as time went on did? Well, runners take some time to accelerate, so they start out not going very quickly, and then they start going more and more quickly. So they're probably going not very quickly to begin with, and fairly quickly at the end. So their actual curve is probably something like that. I don't mean that to be vertical at the end, that would be infinite speed. So where are we looking at this 8 meters per second? What is that? That is the slope of the line between this point and that point, like y2 minus y1 over x2 minus x1. So that 8 meters per second, we can draw a dashed line. Not that they actually ran exactly like that, but this slope, it was 8 meters per second. So here's the big question, and this is their actual position curve. And here's what their position curve would have been if they were running a constant speed that whole time. So the big question is, was there ever a time when they were going exactly 8 meters per second according to their actual position curve? So take a look at that. Can you spot a time when they might have been going exactly 8 meters per second? Well, 8 meters per second is a slope, so we could say take this slope or take this line and shift it down until it exactly is tangent to the curve. And at that point, I'd say that's about here, the tangent line would have a slope of 8 meters per second. I'm not saying everywhere on the curve, but just at that place, the tangent line would be parallel to this other line I guess that's kind of parallel the way I drew it. So was there ever a time here when the runner was going exactly 8 meters per second? I'd say yes, it's right around there. And I'm getting that 8 because that's what their average speed over that whole time period was, not just arbitrarily picked the number 8. So the mean value theorem says that there is a time, or an x value, where the derivative, the slope of the tangent line, is equal to the slope of a line that goes from where you were at the start to where you were at the end of the time interval. So we can say there exists a time, or you could say an x value, and we're going to name it c, between your start and end time. We'll say your start time is a and your end time is b. Such that the derivative at c, so we're saying here is times c, such that the derivative at c is equal to the average speed on the whole interval. And how can we write the average speed on the whole interval in calculus E notation? Well, we'll say average rate of change of f of x on the interval a to b from start to end. How can we write that? Well, that's just our difference quotient on this non-tiny chunk of time. So end value minus start value for y values over the elapsed time, or the amount of x. So how can I write this using function notation? Take a sec to write that yourself. That would be end y value minus start y value over end time value, or x value, minus start x value. So that's the conclusion of the MVT, but is it always true the way I've stated it? It turns out there's some exceptions, and I want you to think about the exceptions, and then we'll start the next video. So I'll just write here, say, when is this true? What has to be true about the function for this to always be true, or what kind of functions break this idea? So see you in the next video.